Alright, so I'm making this quick video to talk about a few things that we weren't able to catch up on in this quiz section. Important idea about crystal structure and Bravais lattice. Always remember this crucial equation, which many people have like fundamental misunderstanding about. Crystal structure is completely different from a Bravais lattice, but they are related with this equation where to make a crystal structure you need a basis and you repeat that basis over a given lattice, and that gives you a crystal structure. So what you might have studied is that examples of these lattices are simple cubic, or which is given as SC, or body centered cubic, which is referred as BCC, and then there's face centered cubic, also referred as FCC. These are the three common cubic lattices. There is also hexagonal close packed, there could be a double hexagonal, but this is not a Bravais lattice. Always remember that. Again, this is a bit advanced to talk about double hexagonal close packing, and then there could be more. And then for bases, what you have is some arrangement. So, for example, you could let's look. So you could have, let's say, one carbon atom, one carbon atom. So imagine taking one carbon atom, and then that one carbon atom is being repeated over any of this given lattice. And you could even have a molecule being repeated. So a molecule of NaCl being repeated over, let's say, FCC lattice, and this could give you a crystal structure of NaCl. So NaCl crystal structure has an FCC Bravais lattice, but FCC is not a crystal structure. Always remember that. People misuse and confuse these two terms, Bravais lattice and crystal structure, and use them interchangeably. They cannot and should not be used interchangeably. So the idea which differs between these three lattices that we have, simple cubic, body centered, face centered, is just how the atoms are arranged, and thus how many atoms are there in one given single unit cell. So let's take an example of a unit cell. I'm just going to draw the simple cubic. In simple cubic lattice, all you have is the atoms or your points at the corner are occupied by whatever material you have. And this is what I'm drawing here. So you can like create or add an atom everywhere. And what you'll notice that each atom here, and again remember this is simple cubic, each atom contributes 1/8, because if you imagine and if you try to visualize this one atom, I'll shade it with blue. This one atom is shared among 8 neighboring unit cells. So there could be one down here, one up here, and then one here, and so on and so forth. So you could imagine and draw out eight different unit cells, neighboring unit cells that share. So each atom contributes 1/8, and there are 8 points. So it's like 1, 2, 3, 4, 5, 6, 7, 8. So in total, you have 8 into 1, 8, which basically gives you 1. So in a simple cubic, you have, if I write total atoms, you have one total atoms. And similarly, you can count and practice with body centered and face centered. With body centered, you will get 2. It's simply one that comes from simple cubic, which is from the corners, plus one that sits in the body center. For face centered, you have 4, where again one comes from corners, one total atom from the corners, and then you have 6 faces. You have yes, you have 6 faces, and each one of them has 1/2 contribution, which gives you 4. I'll write faces over here. All right, cool. And it is always really good to remember this relation of total atoms and simple cubic, BCC, and FCC. Now, one important thing that which is a crucial term to understand and to appreciate is atomic packing factor. And what we just referred up about total atoms is a way of using and saying the same factor number, where this atomic packing factor, or referred as APF, is a number or a percentage which is basically telling you how much volume of unit cell is occupied by the atoms. So because here atoms are considered as spheres, and they do not fill up the entire cube that you have of your unit cell, you can have a percentage of how much are you filling, and different unit cells have different filling. FCC. Now one of the important things here is to define the formula for this. So let's write that down. So the atomic packing factor can be given as volume of all atoms divided by volume of unit cell. So it's just a ratio, or you can even write it in percentage form by multiplying it by 100, and that'll give you percentage. Or if you want a factor, just keep it in this form, it'll give you factor. Now, the denominator here, the volume of unit cell, because it's a cube, it'll just be equal to A cube, where A is side length. Correct. So again, if you remember high school geometry, this is a cube. If your side is A, then the volume of this becomes just A cube. For the volume of your atoms, what you need is total atoms, and then you have to multiply it by volume of one atom, right? So because again here atoms are sphere, and if you remember again high school geometry, volume of a sphere is 4/3 pi r cube, where radius is the radius of that sphere, and let's call that total atoms by the number small n. So this will give you the volume of all atoms. I should write here all. And then when you solve this, and again remember n for simple cubic, n will be equal to 1. For base centered cubic, n will be equal to 2. And for face centered cubic, n will be equal to 4. You put that, you solve it, the atomic packing factor get is highest for FCC, around 74%, and then BCC is around 52%. And then I will recommend solving for the simple cubic case. It should be pretty simple. You have to put the values in the formula. And an important thing that we need to understand from this point is how to relate the side length A of your unit cell with the radius R of your atom, right? So let's take a simple example of BCC. So let's draw out a rough body centered atom. I'll just draw the cube first, so I have points to locate, and then let's draw. So you have 1, you have 2, 3, oops. You have 4, you have 5, you have 6, you have 7. And then in the back, again, remember each corner has 1, and then there's one dude sitting at the center, right? And then there's like this dude sitting at the center. So to find this relation, what you have to do is somehow take these radius of these hard spheres, and then A, which is the side length of this unit cube, and develop a relation. What you can use is just simple trigonometric relations to find this value. I'm just going to use an example here that we have in the slides. And again, this is a very nicely drawn picture, so it'll be much easier to work with. So we'll start with the base that we have. So take this side and then take this side and take the diagonal of this base, and which is given by this blue. I'm going to mark it with the red line. So this red line. So this becomes a right angle triangle, and you get this value as root 2 times A. And then if you take the body diagonal, which is the longest diagonal, and this one side, again, so this is, let's mark it with some different colors. This is A, and then we know that the other one is root 2A. So the guy with the yellow color, that will become root 3A as shown here. And if you try to visualize it carefully, you will see this root 3A of the body diagonal consists of 3 hard spheres touching each other. And what is important, you have a contribution. Let's try to write it down again. So you have a contribution R from this one sphere, R over here, and then R over here, and R over here. So if 1R, 2R, 3R, 4R. So what you have is in total 4R, which is equal to root 3A. That gives you A equals to 4R divided by root 3. And this is a very important relation. And again, remember, this is for the BCC. I will highly recommend you to practice how to find the same relation. So let's write this down here. For BCC, we just found A equals to 4R by root 3. And again, remember, here A is the unit side length of your unit cell, or the side length of the unit cell, and R is the radius. We are assuming that the atoms or ions or whatever these balls are representing are literally touching each other, which is not what happens in reality, but that's a nice assumption at this level of precision. What I'll recommend is try finding the same relation or a similar relation for face-centered cubic, where relate A with R, and you'll get a similar formula. It'll be a bit different. It's much easier when compared to the BCC, because all you need is just one face, and you will see that you can just pick any face and take the diagonal of that face. So I'll just write it here. Take face diagonal, and then you'll have three spheres touching, and then you can establish the relation between the phase diagonal and value and the three spheres, and you can test it out. Now, why is this important? Because again, when you look at the atomic packing factor, it'll be crucial to understand when you write volume per atom what to put in there, and then atoms per unit cell and the atomic unit value. And then you can calculate for FCC, BCC, and other structures. We are only focusing on cubic structures, but there are many other structures that you could look into. Following this is another important and last topic in this section is something let me correct my spelling. Theoretical densities. Mostly we'll be focusing on theoretical density of metals. Again, it's a rough concept which you could apply to some other systems, not always, but sometimes. And these all serve as very good approximations to different situations, and they work to a precision that is good enough for most of the time. All right. So again, keep in mind this is a theoretical calculation, and if you remember from your I don't know, like your chemistry or physics days when you studied physics 101, chemistry 101, density is nothing but the most fundamental definition, mass upon volume. All right. So how much mass is stored and how much volume gives you the density. You can have the units of gram per centimeter cube or many more. This is the SI unit representation, I would say, or the most common representation. Cool. So here what we have to do is calculate the theoretical density of metals in the atomic perspective. So one very important formula that pops up is this over here. I highly recommend to go over this. And again, you could write here weight over volume. That's a more robust definition instead of using mass over volume. Because again, mass does not take into picture the gravitational pull that a body faces. But yeah, so weight is a more refined definition. So yeah, keep in mind there are four terms associated. You have n, small n, which is again the atoms per unit cell that we calculated. Remember, for simple cubic, this becomes 1. For base centered cubic, this becomes 2. For face centered cubic, this becomes 4. All right. And then you have capital A, which is your atomic weight in grams per mole. So if you remember, this was the same thing that we calculated as the weighted average in some of the previous sections. Now, you won't have to calculate this every time for all the isotopes, but it'll be just given to you most of the time. And you can just use your literature or, internet to find this value. And the denominator, what you have is the VC, V subscript C, where this is the volume per unit cell. So not the total volume, but volume per unit cell. So what is the volume of one unit cell? Which will simply be just A cube. The question would be expressing this A in terms of R. And that is what will vary with every new lattice. So for simple cubic, it will be different for base centered, and that's what we just derived. And I would recommend you practice with that. And this last term is nothing but like a constant, which always remains the same, is the Avogadro's number. 6.022 or 23 into 10 to the power 23 atoms per mole. Interestingly, if you very carefully see, the units will all perfectly match up and finally give you units of grams per centimeter cube. And you can do that dimensional analysis for just like a satisfaction and clarification. And here's a very nice example. Try it at home if you want to. Is looking at copper. FCC structure. This is given as n, small n, the 4 atoms per unit cell. Again, we remember FCC has 4 atoms. The atomic weight is given 63.55 grams per mole. The radius in nanometer is given, and you have to compute the theoretical density. Use the formula given above, just put in the values, and what you will find is that it is 8.89, which is super close to the actual density, 8.94. And that's why these hard sphere models or these approximations work pretty well in actual situations. Cool. And in the problem statement for the quiz section, there is a nice example of doing it for a BCC structure. So the copper is for FCC. The BCC also nice and easy, where it's a bit math intensive. Instead of just directly calculating the theoretical density, we give you that theoretical density. So if this is the formula over here, right, what you have is you have the theoretical density given, you have the small n given, you have the atomic weight of tantalum given, you have the Avogadro's number given, and this Vc, which is again, remember, volume of the cubic unit cell. Because it's a cube, it should just be a cube. For BCC, we know that a equals to 4r by root 3. So if you cube this dude, a cube will just become 4 cube is 64, r cube, 3 cube, the root 3 cube would be 9 root 3. And then you can just take in and put these values in. So again, focus on this formula. This is the important formula. And then it is just doing careful algebraic mathematics. And I'm expecting and hoping that you guys are comfortable with that. If not, just feel free to come to office hours to discuss that. And you have this equation, all the values are given to you. What you need to do is just find r, and then when you just like write all that math, intensive math, you will get something like this. Highly recommend you to try it at home. You could also think about this problem in sort of a backward direction, where right now in the previous problem I gave you that this is a BCC system. But what if I do not do that? I will give you the density, I will give you the atomic weight, I will give you the radius through which you can calculate the unit cube volume, and you know the Avogadro's number. So in this system, what you will do is calculate small n. And again, remember, what is the small n? This small n is the number of atoms per unit cell, right? And this is what will differentiate if it's a BCC or if it's an FCC. So you could take it two routes. What if it's BCC and what if it's FCC? You could, the n would be 4 in FCC, the n would be 2 in BCC. Compute this thing, compute the density. Similarly, compute this thing, compute the density. And then just compare that value, and you will find out that it is the closest when it is BCC. So this is the correct structure. All right. And again, you can practice these questions at home with the slides, but a few fundamental understanding is required, and that's why I wanted to put this up. I'll write this formula again. Rho equals to Na divided by volume of cubic unit cell multiplied by Na. Please review this formula. Very, very helpful. Gives very nice accurate value and precision. N is, oops, sorry. Let me disable this. N is nothing but atoms per unit cell. Atoms per unit cell. Your A is atomic weight. V subscript C is volume. You could call it volume per unit cell or volume of one unit cell, which is basically A cube because you're talking about cubic. And n subscript a is nothing but Avogadro's number, which is a constant, which we know is 6.02 into 10 to the power 23. And then you can check all the units. Please always keep the units in mind. Many people screw up the units. We do not want to do that. That is one of the most fundamental mistakes people make and screw up their assignments, exam questions, and even like actual calculations. There was a big issue with the space program because they had messed up some of their units in the calculations, and the entire program got fucked up. So, yeah, this was all for the crystal structure and Brava lattice that we'll need for the next quiz.